Welcome to This Explainer. We are diving straight into what is arguably the ultimate cosmic mystery. Why does time only move in one direction? I mean, we schedule meetings, we celebrate birthdays, we watch the clock tick by every single day. But beneath all of our daily routines lies this fundamental puzzle that has literally kept physicists awake at night for generations. You know, it all starts with a simple, everyday question that actually hides a massive paradox. We all intrinsically know the past is fixed, right? And the future is up for grabs. We remember yesterday, but we definitely don't remember tomorrow. We're born young and we inevitably age. Time has this stubborn one-way direction, which physicists call the arrow of time. Because here is the really crazy part. While our everyday experience tells us time always moves forward, the fundamental laws of physics actually don't distinguish between the past and the future at all. If you think about space, and imagine floating out there in a spacesuit, there's no intrinsic difference between up, down, left, or right. And in the deep down equations of physics, from general relativity all the way to quantum mechanics, time behaves the exact same way. The equations work perfectly well forwards or backwards. So where on earth does this arrow come from? To solve this, we actually have to look at an incredibly unexpected place. 19th century steam engines. From Sadi Carnot studying steam engines in 1813, to Rudolf Clausius coining the term entropy in 1865, and finally Ludwig Boltzmann solving the probability puzzle in the late 1800s. These engineers were just trying to build better, more efficient machines, but their practical quest accidentally unlocked the deepest secret of the universe. So, the crucial takeaway here is that physicist Rudolf Clausius realized energy naturally spreads out over time. He formalized this concept as entropy. We hear entropy described all the time simply as disorder, but it's actually much more accurate to think of it as the natural tendency of energy to become dispersed. The total amount of energy in the universe stays constant, sure, but as things happen, that energy becomes less concentrated, more spread out, and inherently way less usable to do actual work. Let's use an everyday example to really picture this. Think of a beautifully structured sandcastle. There is only one specific way to arrange those grains of sand to build that castle, but there are trillions of ways for the wind to scatter it into a messy pile. If you leave it out in the desert, the wind will eventually blow it into a flat, featureless mound. The sandcastle is what we call a low entropy state because it's highly ordered. The pile of sand, that's high entropy. Now, there's absolutely no law in physics that says the wind couldn't spontaneously pick up a pile of sand and drop it perfectly into the shape of a majestic castle. It's just overwhelmingly, almost impossibly unlikely to actually happen. You get the exact same dynamic with the Rubik's Cube. When the cube is perfectly solved, it's in a highly ordered, low entropy state. But close your eyes and just start making random turns. You aren't violating any fundamental mechanical laws of the cube by scrambling it. You're just inevitably moving it from an incredibly rare, specific configuration into one of quintillions of messy, common ones. Ludwig Boltzmann proved this whole concept is literally just about statistical probability. He found that in a tiny, microscopic 8-atom system, heat actually has a 10.5% chance of flowing backwards from cold to hot. Imagine taking two tiny metal bars, one with more energy packets, one with fewer, and touching them together. The energy packets hop around randomly. Because the system is so unbelievably small, there's roughly a 1 in 10 chance that at any given moment, the hot bar actually gets hotter and the cold bar gets colder. Meaning, it is not physically impossible for energy to clump back together. But watch what happens when you scale that system up to just 80 atoms. Suddenly, that probability drops to almost zero. A chance of 0.05% is tiny. And remember, in a real, everyday object, like a hot cup of coffee or a solid block of metal, there aren't 80 atoms. There are hundreds of trillions of atoms. The mathematical probability of their energy suddenly clumping back together to spontaneously heat up your cold coffee is unfathomably small. It just isn't going to happen in the lifespan of the universe. And that overwhelming statistical inevitability, that is exactly why time only runs in one direction. Now, this brings up a massive, absolutely fascinating question. If everything in the universe naturally decays into disorder, how do complex things like the Earth and biology even exist? If the universe is a one-way street toward breakdown, how are there trees, animals, and cities? Well, we have to rethink our relationship with the sun. If you ask most people what the Earth gets from the sun, they'll confidently say energy or heat. But here's the catch. Earth doesn't just store up energy. It takes in one highly concentrated photon from the sun and radiates 20 lower energy spread out photons back into space. For most of Earth's history, the total amount of energy we receive from the sun is basically equal to the amount of energy we radiate back out into the cold void. If we didn't do that, the Earth would just continuously heat up until it melted. So if the energy perfectly balances out, what is the sun actually providing us that makes life possible? The secret ingredient the sun provides isn't just energy. It's a constant, steady stream of low entropy that prevents our planet from reaching a boring, dead equilibrium. The energy we get from the sun is highly concentrated and bundled up. It's super useful. Plants capture this concentrated energy, use it to build sugars, and then animals eat the plants. Literally every single thing happening on Earth, from a tiny leaf growing to a massive hurricane forming, right down to you breathing at this very moment, is the process of taking concentrated low-entropy energy, using it, and discarding it as dispersed high-entropy thermal waste.
And here is where it gets really wild. It turns out life itself might exist because it is spectacularly good at accelerating this natural tendency. Biology acts like a machine that rapidly converts concentrated low entropy into high entropy. Look at the surface of the ocean, for example. Seawater that contains cyanobacteria and organic matter actually produces between 30 to 680% more entropy than sterile seawater. Life absolutely does not violate the second law of thermodynamics. It actively champions it.
Physicist Jeremy England summarized this beautifully. He says, "You start with a random clump of atoms, and if you shine light on it for long enough, it should not be so surprising that you get a plant." Think about that. Biology isn't a fight against entropy. If you blast a random clump of atoms with low entropy for long enough, nature naturally favors the evolution of complex structures, like a plant, simply because those structures are incredibly efficient at spreading that energy out. Okay, but if life completely relies on the sun's low entropy, we have to look backwards to discover where the universe originally got its concentrated order. Think about it. If yesterday had lower entropy than today, and last year had lower entropy than yesterday, we have to trace this all the way back. Where did the ultimate source of low entropy, the original starting battery pack of the entire cosmos, actually come from? Well, physicists call the answer to this the past hypothesis. It tells us that 13.7 billion years ago, right after the Big Bang, the early universe was in an incredibly unlikely low entropy state. Now, I know that sounds super counterintuitive. The early universe was a hot, uniform soup of gas, which usually means high entropy. But you have to factor in the crushing, overwhelming force of gravity. Because matter intrinsically wants to clump together into galaxies, a perfectly smooth, uniform distribution was actually an exquisitely rare, balanced, and remarkably low entropy starting point. Get this, the very early universe contained just a microscopic fraction of the total entropy that it has today. It possessed roughly 0.00000000003% of the entropy we see now. That unbelievably pristine starting condition is literally the only reason anything interesting has ever been able to happen. Everything, from galaxies forming, to stars igniting, to life evolving, is just the universe slowly spending that initial reserve of low entropy. So where is all that entropy going today? As the universe expands, supermassive black holes act as the ultimate cosmic vaults, holding almost all of the accumulated entropy. Back in the 1970s, Jacob Bekenstein and Stephen Hawking completely shocked the physics world by proving that black holes aren't just empty voids. They actually have a temperature, they emit radiation, and they hold entropy right on their event horizons. In fact, they hold almost all of it. All the black holes combined hold roughly 3 times 10 to the 104th power Boltzmann constants worth of entropy. That is an absolutely staggering amount, driving the universe irreversibly toward an eventual heat death. To put that into perspective, the supermassive black hole at the very center of our Milky Way alone holds 1,000 times more entropy than the entire early universe did. Trillions of years from now, when those black holes finally evaporate, the universe will reach maximum entropy, total equilibrium, and the arrow of time will essentially disappear because nothing will ever change again. I know that ultimate heat death sounds kind of bleak, but don't let it depress you. Think of the universe exactly like milk mixing into a cup of tea. Both the unmixed beginning and the fully mixed end are actually quite simple and boring. Before you pour the milk, the tea is perfectly uniform. It's low entropy, but it totally lacks complexity. Then, if you wait long enough, the milk fully mixes in. The whole cup becomes a uniform beige. It's high entropy, but once again, it lacks complexity.
It's just featureless.
We exist right in the middle of this cosmic mixing process. And that middle phase is the only place where beautiful, intricate, and complex structures can emerge and thrive. As the milk first hits the tea, it creates incredible swirls, dynamic currents, and beautiful temporary patterns. That is exactly what our universe is doing right now. The stars, the planets, you and me. We are the intricate swirls of milk mixing into the cosmic tea. We are complex structures feeding off the universe's grand transition from order to disorder. Since we find ourselves in this incredibly rare, fleeting sweet spot of cosmic complexity, the real question to take away from this explainer is how you are going to use your moment. Time's arrow guarantees that our existence is a temporary phenomenon in the grand timeline of the cosmos. But rather than being a sad reality, it highlights how profoundly special this era of the universe actually is. You have a finite amount of low entropy to consume and dissipate in your lifetime. So, how will you organize your atoms, share your energy, and make your mark before the universe mixes completely?